Hello, everyone. Go ahead and ask any questions you might have while we're waiting for the rest of the people to get in. Time has started or has it's time for start class already. To start class already. That's what I was trying to say. So we're going to start in a few minutes either way. But if you have any questions about policy, classes, particular homework problems, particular practice test problems, anything like that. I was going to use this time tonight to go ahead and start in another chapter, or actually do the chapter on Faraday's law. But I decided, since y'all had such a long break, it might be better for me to just offer a couple examples of problems that we've done in the past, or problems that other students have asked about, and just to get you up to speed or back in groove or whatever. So now's the perfect time if you have any questions, like practice test questions or homework questions, to bring them up. Other than that, I'm also going to just work the ones I prepared about working in class the other day, because various students asked for me to do it. I will remind you that you are allowed an equation sheet on the midterm. The equation sheet is supposed to be limited to equations I specifically gave you, which is like that integral form of Coulomb's law and that integral form of Biot-Savart law. I gave you a version of that that's quite different from your book, a little more detailed than your book. Those are certainly allowed, and I recommend you have them, because I suspect you're going to have to do something like that. And of course, either that or something like a Gauss's law and Ampere's law type problems. You're going to have to be able to do those, voltage calculations, that sort of thing. But other than that, it should just be the problems listed in your textbook that on the right hand side edge or whatever, it'll have like parentheses 8-8, which would be like equation 8 in chapter 8. So if it has that little parenthesis with number in it, then you're allowed to put it up there. I saw in the 241 section of the class, there was one area where they had two equations you guys probably remember, namely that the static friction is less than or equal to mu static times the normal force, and then the kinetic friction was equal to mu kinetic times the normal force. Neither of those actually had numbers associated with them, but they had on the right hand side static friction in square brackets. So if you see something like that, you can err on the side of me allowing that. So hopefully somebody might actually watch this tonight and get that, even though they came in late. So I'm going to, since it appears no one has any real questions for me, I'm going to go ahead and get started on some examples that I think are worthwhile. I'm going to start off by just reminding you of some of the major things that we do in this class and that I expect you to be able to do. In other words, this is something that could very well pop up on your midterm. And if it doesn't pop up on your midterm, it's even more chance for you to suspect it's going to pop up on your final exam. But you might not have thought that we'd necessarily do it, even though I've been sort of advertising that you're going to be responsible for it for some time. The time parameters for the exam. Well, I have asked that everyone begin their exam. Oh, actually, that was face-to-face. Yeah, you're in this class. So the class will allow basically an hour and 50 minutes. 1 hour and 50 minutes is how long you'll be allowed to take the final. No one suggested they couldn't stay that long or whatever. I have a couple of students that actually wanted to take it at the testing center as opposed to using their webcam and Respondus lockdown browser with Respondus monitor on it. Anything else, Matt, or anyone else? As soon as I get this camera off of me, I'll stop yawning. Weirdest thing.
Oh, yeah, I had a quick question, Professor.
Yeah, go for it.
I saw the practice exam. I know the due date said that it was tomorrow. Are we still going to be able to take that on Thursday? Like, I was planning to take it several times Thursday before the exam.
Yeah, I must have did that by accident, forgetting that you guys are a Tuesday, Thursday class. But yeah, I'll make it normally it's not supposed to disappear until the time for your test to be over. So for your class, it should disappear at 8 p.m. So Let me write that down so I remember. All right, I got that written down, so hopefully I won't forget that. All right, so what I'm going to do now, if no one has any more, well, you can still ask me questions if you want. I'll put it that way. But since no one seems to have any questions, I'm going to go ahead and share my screen with you guys as soon as it allows. Okay, so we had this happenstance, and I designed it that way on purpose. Okay, the textbook designed half of it that way, but the other half I chose to do it my way. So what we learned first was Coulomb's law, which was quite simple. It basically said that the force on an object or on one object due to another object as a result of their charge was equal to Q1, Q2 over 4 pi epsilon naught R squared, where R is the distance between the infinitesimally small point charges Q1 and Q2, are the spherically symmetric charges, and the distance is from the center of one spherical charge to the center of the other spherical. That's the distance. And of course, the force is either attractive or repulsive. And it's, of course, attractive if the two charges are unlike, in other words, one positive, one negative. But if they're alike, they're repulsive. Then I told you how we did not like the idea of forces reaching out over space and grabbing a hold of things and pulling them without us seeing any kind of tethers or anything. So we conjured up the idea. Oh, what is wrong? I'm not going to stop yawning. So we conjured up the idea of a field. And what we did is we said, okay, well, let's imagine instead of there being a force on Q1 due to Q2, so the force on Q1 as a result of Q2 would be F12, and that would be again Q1, Q2 over 4 pi epsilon naught times R squared. But what we could think of it as if there was an electric field created by 2, which was Q2 over 4 pi epsilon naught R squared. This would be the E field, at least its magnitude. And then all you had to do to get the force is multiply it by the charge you plan on putting there. And that ultimately became what we were using as our electric field. I amped that up a little bit by giving us a differential form. And my differential form is the differential element of the electric field is in fact dq over 4 pi epsilon naught RP minus RdQ to the third power times RP minus RdQ. And what that all represented, of course, was if you imagine a three-dimensional coordinate system and you imagine that you wish to know, for instance, the electric field at this point right here, P, then this vector would be called RP. And if the little bit of charge causing the electric field was a little infinitesimal charge element right there called dq, then there would also be yet another vector pointing from the origin to the charge dq, and that vector would be r dq. Therefore, the vector that goes from let's say here to here. Whoa, let's not do that crazy thing. This vector right here is in fact RP minus RDL. Okay. So in other words, by subtraction, we could actually find a vector whose length is exactly the desired length for the, I'm trying to move this thing and it's not happening. That's not it either. That's not it either. That's not it either. Oh, well. Okay, well, the vector whose length is really the R in the Coulomb's law formula. And now we actually have a direction for that as well. That direction is the same as the RP minus RDL direction. Again, this red vector that I just draw should start at the head of the black vector RDQ, but for some reason it automatically connected it at that other spot, and I'm trying to get it to move that, but it's not being very cool about the whole situation, being kind of a jerk. So let's see if I can get rid of some of these dots at least. So what I'm trying to do is just at least click on this sucker so I can go ahead and move it. Nope, that's not it. Click on that way. Nope, not that way either. Okay, oh well. Well, see, it keeps doing that, and then it's like I can move it, but there we go. That's cool. Okay, now what I'll do is I'll just fix that other little vector. Put an arrowhead there. All right, so now we got this picture again. There's our XYZ coordinate system, and that's the differential form of Coulomb's law, so that we can use it for integrals. I'm getting ready to work in 2 examples on that. But what we discovered was, yeah, that's a way we can do it, brute force, and there's very few problems we can do that solved using this, at least by hand, in terms of calculating with, you know, tricks of integration and stuff like that. In fact, the vast majority of the problems in the real world would require us to take and write code to mimic either this integration process or take the differential equation that's the equivalent of Coulomb's law, or something that you could actually use to derive Coulomb's law from. You could take that and solve it as well. But again, both of those are requiring computers solutions, or at least computers to solve it. There are, of course, some Gauss's law problems you can actually solve by hand, but they're, again, few and limited. So Gauss's law was, in fact, oh, I shouldn't write it that way. I'll write it the integral way. Is the integral of E dot dA is equal to Q enclosed over epsilon naught. And what that was it was a integral with a circle on it, and that circle meant that you had to integrate over a closed surface. So this circle just means it's over a closed surface, and we know it's over a closed surface because the differential is a differential area. It's dA, not dL. Later, when we do Ampere's law, we'll have a similar integral with a circle around it or on it, and that circle means you're going to integrate it over a closed circle or a closed path. So for instance, you can imagine basically any way you can tie the ends of a long string together, that would be a fair thing to integrate along in Ampere's law. So that was our big scenario. Is one, you had to be able to find an electric field either by doing simple calculations with that E field, the equation mark E dash field. If you're just point charges, you can add up any number of point charges that way. Or if they're spherically symmetric charges, then as long as you treat the distances with the realization that the charges are actual spheres instead of point objects, you can just add them up algebraically in principle for any number of them. But when you get them infinitesimally small, you have to take an infinite sum. That requires you to use this equation, which is the one I said you can put on your equation sheet, even though it's not in the book. Okay. And then if you're really lucky, you can avoid both of those steps and use Gauss's law. And the deal with Gauss's law is that we chose a certain set of symmetries. You had to either have infinitely large disks, flat disks, or you had to have infinitely long cylinders, or we had to have a sphere. So it had to be like a solid sphere, a spherical shell, something like that. So you had to have spherical, cylindrical, or infinitely planar symmetry. When you had that, then you could use Gauss's law to extract that E in the closed integral of E dot dA, because the left-hand side will in fact always work out to be the electric field as a function of some variable times area. So you get like E of R, meaning E only depends on the variable R, times 4 pi R squared, because you did it for a circle, and the volume, or excuse me, for a sphere, and the volume of a sphere's surface, excuse me, the area of a sphere's surface is 4 pi R squared. Or you get, if it's not that on one surface, then you actually get like 0. Okay, so that's how we were trying to use that. Then after that, we ultimately got to magnetism, and there was this law called the law of Biot-Savart, and that Biot-Savart law basically said that dB was in fact mu 0 I over 4 pi. I think somebody just came in. It looks like a little minute. Oh, there it is. Okay, there and there. Mu 0 I over 4 pi times dl cross. In this case, I did RP minus RDL over the magnitude of RP minus RDL. Again, a 1 over R squared law that we represent it like as a 1 over R cubed law, strictly because by multiplying by a whole vector, we're increasing its magnitude by a factor of that vector's length. So to get rid of that effect, we have to divide out that magnitude's length. So it becomes a what looks like a 1 over R cubed law instead of a 1 over R squared law. So this is the law of Biot-Savart. This too has a diagram associated with it. Let me draw that diagram now. I'm going to say, you can imagine an axis this way. You can imagine an axis this way. You can imagine an axis this way. Let's say, oh, that wasn't cool. Let's say that you have a certain current carrying randomly shaped wire with a little bit of differential line element right here, which we'll call DL, and it in fact points in the same direction as the current I travels. Then we're going to have a vector that points from the origin to it, and that vector shall be called R sub dl. And then over here is a point in space at which we wish to know the magnetic field. So in fact, there's a vector pointing from the origin to it called R sub p, because that point is called P. Now I think you can see that the actual RP minus RDL is clearly this vector right here. Okay. And I will work an example of that as well this evening, just to get you back up to speed with that, make sure y'all are knowing how to do that. But like happened with Coulomb's law, we ultimately were faced with solving this problem in many sort of complicated scenarios. But again, we were quite limited on the number of ones we could do with just a regular integral and tricks of integration process. In fact, the vast majority of problems, if you wanted to use this, are the differential equation version of Maxwell's equations, you'd have to basically write code to either do the integral or code to solve the differential equations. But what we came up with as a slightly easier way of doing things was, in fact, Ampere's law. And Ampere's law said that the closed integral of B dot dl was equal to mu 0 times the current enclosed. So this is, again, a closed integral, but it's over a closed path. This one up here was a closed integral, but it was over a closed surface. In other words, a surface that had a clear inside and outside. We work with this B dot dl with certain symmetries. So for instance, an infinitely long cylindrical wire works well. You could, in principle, work with a infinite cylinder, also somewhat of spherical stuff. But what we mainly did was we worked with solenoids, toroids, and an infinitely long straight wire. And when we did it, what we came up with consistently was, if those symmetries were present, then we could get some magnetic field as a function of something like r or theta or phi times a length. Or you could have +0 for some other terms. So that's what consistently the left-hand side became in both Gauss's law and Ampere's law. And that made it, at least with certain, if the symmetries were present, it made it a lot easier to solve a lot of problems. Okay. So in this test, which goes up through the midterm, goes up through chapter 28, that means, yeah, Biot-Savart and Ampere's law are fair game. Also, Coulomb's law, and in the F equals Q1, Q2 over 4 pi epsilon naught R squared form, as well as in the electric field, Q over 4 pi epsilon naught R squared form, as well as in the differential, or excuse me, the integral form of Coulomb's law, the dq times rp minus rdq, close parentheses, over 4 pi epsilon naught, magnitude of rp minus rdq cubed. Those are fair game, but you can also expect to see Gauss's law, where I tell you to either use Coulomb's law or Gauss's law to find an electric field, then use V equals the negative integral at E dot dl to compute the voltage difference between two parts of these charged things. And then knowing that voltage difference from those two differently charged things, calculate the capacitance of that body that's made up of two parts. Like for instance, we did a infinitely long cylindrical shell around an infinitely long cylindrical wire, and we assumed the inner wire had a positive charge, say, and the outer wire had a negative charge, and we could calculate the electric field inside the inner wire, between the inner wire and the shell, inside the shell, and then outside of the shell. And then we could integrate from the inside of the inner shell to the outside of the outer wire, or to the outside of the wire, and use that to calculate the capacitance of that coaxial cable. So that's a sort of what we call a capstone problem that allows me to see that you can do all the stuff. So that's something that, again, if you don't see it on the midterm, you can almost be certain it's going to be on the final. So you should know how to do that. Ultimately, we didn't get this far, though. You would do the same thing with Ampere's law that you can do with Biot-Savart, except instead of using V equals the negative integral at E dot dl, we're going to calculate the magnetic flux, which is indicated with a capital phi or phi. That magnetic flux is the integral of B dot dA. So it looks like the left-hand side of Gauss's law, except a B in there instead of an E. When you do that, you calculate that flux, then you can divide that flux by the current taken or driving the solenoid or whatever you're doing, in which case you get the inductance. So that's another problem that ultimately will pop up, but we haven't gotten far enough to do that. Anybody have any questions about that? You are allowed to have constants, of course, on your equation sheet. The one thing is no, you're not really supposed to have words and sentences on it, right? Because sometimes one of the quote unquote chucker questions we'll put in a test is, state Newton's second law of motion, or state Gauss's law, or state Lenz's law, or something like that. So if you go around with an equation sheet that has things named, or whole sentences that could tell you how to do certain problems, then that would be more of a cheat sheet than an allowed equation sheet. Okay. But like I said, you are allowed to have constants on your sheet, and I don't require a minimum or maximum number of sheets. So if you have 5 pages of equations, that's certainly fine. But when you use your camera, as you will when you're taking the online Respondus monitor test, you'll take your camera and hold it up and show me your workspace down by where your feet will be, everything that you can lunge and reach basically, and laid out on your workspace should be, if you have 2 pages of notes and 1 blank sheet of paper, you should have them laid out separately. And then with the camera watching, pick up one, and then show the camera both sides, pick up the other, show the camera both sides, pick up the other, show the camera both sides, show your photo ID next to your face. If it has a number on it, like a driver's license number or social security number or something that you don't necessarily want people knowing, then by all means cover that number up. I just need to see your face on the photo ID, government issued photo ID. I need to see your face with your name on that ID, and then need to see your face next to it, so I can tell that you are in fact the person named in the class and named on the ID. All right. Any questions about that stuff? Okay. So there's a question. Yeah, go ahead.
I don't know if you already said this, but when is the midterm?
Tomorrow at class time.
Okay.
And there's a caveat to that. I said at class time, everybody's supposed to either be able to start early or stay late. I think you've already had labs, so that shouldn't be an issue if you're choosing to stay late. But basically, I need an extra 30 minutes for you, so you can have an hour and 50 minutes.
Did you just say tomorrow?
I did Thursday. I did say tomorrow. Sorry, I meant Thursday.
Okay.
Which one had heart rate monitor on, you guys? It's gonna be Thursday. You can start up to 30 minutes early or finish up 30 minutes late, or you might start 20 minutes early and finish 10 minutes late. That's fine too.
What if we're taking it at the testing center?
At the testing center, I will have a separate test made for you, partly because you might not take it at the same time, and there could be some cross communication between you and the students that have already taken it, or between you and students that haven't taken it after you've taken it. So it'll be a different version that you get. You just have to fit their hours into your schedule.
Okay, so it doesn't really matter like what day we do it, as long as we do it relatively soon.
Normally I expect it done on the same day. So if you can do it on Thursday, that's the best case scenario. But what I normally do is I'll allow Thursday and Friday as the 2 possible days.
Okay, because I needed you need 48 hours to schedule with them.
Is that they're asking for 48 hours in advance?
Yeah.
Okay, well, I would go ahead and call them immediately after this class, or maybe even during the class, and try to schedule something for Thursday. But like
okay, I'll try.
All right. You can also send them an email. That might be the most reliable way, because I think even when they have people not working, they still have people looking at their email. All right. So there's a couple problems to solve. One of which is, let's see if we can calculate the actual electric field a distance over a flat circular disc. Okay, that's a problem that one of my students asked me about. In order to do that, that was one of the weird ones where I didn't use my cute Coulomb's law. That was one where I used Coulomb's law to calculate the electric field over a ring as opposed to a plate. And then I differentiated, in some sense, the answer to that to solve for the plate. So I'm going to do those 2 problems. I'm going Imagine we have a loop of wire with a positive charge Q on it, say uniformly distributed, and we're going to calculate the electric field some distance above the center along the symmetry axis of it. So let me draw a picture of that so you'll have some idea what I'm talking about. So what I'm going to do is I'm going to have an axis like this, x-axis like this, and a y-axis like this. And I am going to assume that we have a ring of charge like this. I will say this object has a total charge Q. Whoa, that's stupid. This object has a total charge Q, and it has a radius, which is big R, and it has a charge per unit length, lambda, that would be Q over 2 pi times big R. And what we wish to know is at a distance Z up here, what is the electric field? Okay. So what I'm going to do with this is I'm going to make use of our differential form of Coulomb's law, which says that dE is equal to dQ times RP minus RDL, or dQ, excuse me, over 4 pi epsilon naught magnitude RP minus RDQ cubed. Okay. Now there's another caveat I didn't give you over there, but I'll give it to you now. dQ can equal lambda times dL, or it can equal sigma times differential area, or it can equal rho times dV. And that is often what we use for Q in Gauss's law as well. So just keep that in mind. All right. So we know what we want to do. We're pretending we know, say, we can pretend we either know lambda, or we can pretend we and R, or we can pretend we know Q and R. I'm going to pretend like we know both of them, which is more than enough information that you need. If you had one, you could get the other, as long as you got the radius. So here's my solution. I'm going to make my solution in blue. So I'm going to first figure out what dQ is. So I'm going to imagine basically there being a little vector that points out here, and then that's out a distance theta, an angle theta, that is. And then I'm going to allow theta to change by an infinitesimal amount to make out this little chunk of material right here that I'm going to call dQ, and that dQ is going to be lambda times R times d theta. Okay, I'm just using the definition of radians from trig to say that the arc length is R times theta. That little wiggle that I did from one red line to the other radial red line is an angle d theta. So this angle right here is d theta, and that's why I have R times d theta is the length of dQ. And then, of course, once you have the length, you multiply that by the charge per unit length to get the actual charge. So dQ is in fact lambda times R dQ. I can say that R dQ is in fact equal to R cosine theta I hat plus R sine theta J hat if I wanted to. I could also just say it's R capital R times R hat. That would work as well. I also know RP points from the origin to the point P, which is where you wish to know the magnetic field or the electric field. So this one is RP right here. RP should be, anyone want to take a guess at that one?
Z in the K hat direction.
Exactly, Z in the K hat direction. So Z times K hat is all we need for that. Now I can calculate RP minus RDQ. That's just going to be Z K hat minus R cosine theta I hat minus R sine theta J hat. So I've now got RP minus RDQ. I think you can see on the page that RP minus RDQ is in fact just that vector right there. And by looking at it that way, you see that basically there are two perpendicular vectors that makes it. One vector that is RDQ and the other vector that's RP, and they're perpendicular to each other. So you might readily reach the conclusion that, actually, I don't want to write that in blue. We might readily reach the conclusion that RP minus RDQ is in fact just equal to the square root of Z squared plus R squared. Now what's going to happen is you're going to do Z squared plus parentheses negative R cosine thetas close parentheses squared plus parentheses negative R sine theta close parentheses squared, and then take the square root of that. But you can see there's a common factor of R squared in the last two terms. You can factor that R squared out and you'll get sine squared plus cosine squared times parentheses around R squared, or excuse me, parentheses around cosine squared plus sine squared times R squared. So sine squared plus cosine squared is 1. That's how you get that square root there. So now we've got all the parts. We just have to go through the actual process. And in fact, if you get this far, you've basically, once you set up this integral, you've done all the physics and the rest is really mathematics. You have a question, or is somebody just talking in the background? Okay, so E, which is equal to the integral of dE, is going to in fact be, let's see, it's going to be integral, I'll put 1/4 pi epsilon out front. It's going to be integral of dq, which we said was lambda r d theta, times z k hat minus r cosine theta I hat minus r sine theta j hat. All that divided by r squared, z squared plus r squared to the 3/2 power, because the 1/2 power is the length and then we have to cube it. Okay. So now I can go ahead and say, well, the lambda and the r comes out in front. So I'm going to say lambda r over 4 pi epsilon naught. You don't see this necessarily right now, but in fact, the z squared plus r squared is also just a constant. So that's coming out in front. And I end up getting the integral of d theta times z k hat minus r cosine theta I hat minus r sine theta j hat. Now it's all to the right of d theta, but that It's just mathematical notation that we use. We're literally going to have to integrate each piece of that. But I think once you realize we got to integrate from theta equals 0 to 2 pi, I think you'll agree that mathematically speaking, the integral of cosine theta d theta from 0 to 2 pi is 0. And the integral of sine theta d theta from 0 to 2 pi is also 0. That is just mathematical. You can tell from the graph of cosine, which starts at 1, drops down to 0, drops down to -1, turns back up, goes to 0, goes back up to the +1 again, where basically the two positives add up to be the exact same area as the whole negative area in between. So they're going to cancel out. And sine, of course, goes from 0 to 1 to 0. That's all positive. Then it goes from 0 to -1 to 0 again, and that's all negative. Those two are going to cancel each other out. But you can also look at this physically. Imagine if you had a DQ where we're saying right now in this diagram. Well, if you add 180 degrees to that theta, you're going to get another DQ that's just like it. And in fact, that one's going to have exactly the opposite X and Y components that the regular DQ had. So those X and Y components are going to disappear, and all that's going to be left is the K component. So there's multiple reasons that we know this integrates to 0, and this integrates to 0. And I'll put that on there, the slash on there, so you'll know I'm saying 0 there. So really all we have is just the integral of d theta. So what I'm going to do now is I'm going to say this is all equal to lambda r z over 4 pi epsilon naught z squared plus r squared to the 3/2 power. And all of this will just point in the k hat direction. And then, of course, the integral from 0 to 2 pi of d theta is just going to be 2 pi. Now you can realize, wait a second, I've got 2 pi times r in the top, and then times lambda. So that, in fact, is equal to just Q. So I can write this electric field a couple ways. Either I can say the electric field is lambda. Whoa, it just switched to racing. The electric field is either lambda times 2 pi r over 4 pi epsilon naught r. Oh, there you go again. Z squared plus r squared to the 3/2. All that times z k hat. Or you can substitute it and say, since lambda times 2 pi r is q, I can just call it q over 4 pi epsilon naught z squared plus r squared to the 3/2 power times z k hat. So that's the actual electric field. And in fact, if I go to do, instead of a ring like I did here, if I go to do a disk, I can sum up the electric field from similar rings to this. And I would say the differential electric field in that case would be, let me get a different color here. I'd say that DE would in fact be equal to DQ times Z over 4 pi epsilon naught Z squared plus R squared to the 3/2 pointing in the k hat direction. Okay. So that's what I'm going to do now. Anybody have any questions on that I just solved? All right, let's do this other one then. Whoa, yeah, there it is. Okay, so I'm going to do the other one. Again, I'm going to draw a coordinate system. And I am going to assume it is a disk like that. And in fact, what I can do is I'll treat that as a differential area element. And then I'll say that's still part of yet a bigger disk, something like that. Okay. So that's the actual disk, is that big outer line that I drew, and this two inner lines are actually just the inner and outer sections of a ring that we're going to deal with. So what I'm going to say right now is that the radius of this disk is capital R. I'm going to say the radius of this inner part of the disk is little r. And I'm going to say that this part right here is dr. And in fact, what that means technically is, if you want to know what that differential area element is, and that is part of what we want to know, we're basically going to call that dq, which is equal to sigma times dA. Well, sigma, since we're going to assume it's uniformly charged, we'll also say it has a net charge Q. So sigma would be Q over pi big R squared. dA is technically equal to, we're going to calculate the radius of the big circle, if you will, the one that has a radius of R plus dr. So we do that area, it's pi parentheses R plus dr squared. And then we're going to subtract the inner part, which is just out to a radius R. So I'm going to put the pi outside of it and just say this is R squared there. Now I'll use the fact that I know how to square a binomial and write this as R squared plus 2R dr plus dr squared minus R squared. Okay, the minus R squared came from that second term. But you can see already that the R squareds are going to cancel out. And what you get is equal to 2 pi R dr plus pi times dr squared. Well, you're taking the limit as dr goes to 0. So dr of this thing, dr squared. So this dr squared is very, very close to 0. That's why we can pretend that the area of this, we can pretend that it's actually going to be 2 pi R dr, because this term is very small compared to the other terms. Now it looks like basically like there's a rectangle like this, whose length is 2 pi R and whose thickness is dr, when in fact, you know for a fact the area, if we were to cut it and lay it out flat, that area would actually be 2 pi R on this side. And then this side would be 2 pi times r plus dr. And of course, this thickness would still be dr. But the main thing is you can tell by those little triangles that they're not exactly equal. But that's why we're allowed to use that in our tricks of integration and stuff like that. So what I've done now is I've actually computed that dq is going to be sigma times dA, and sigma times dA is sigma times 2 pi r dr. So using my previous result, here's my solution. E is equal to the integral of dE, which we said right here was z dq over 4 pi epsilon naught times z squared plus, I'm going to now say r squared with lowercase r here to the 3/2 power. And all of that, of course, would be in the k hat direction. Okay. So now I can work through this process and say E is going to be equal to, the Z can come out in front, as can the sigma. And then I'm going to have the 4, the pi, the epsilon naught out here. That's pretty much all I'm going to put out here for right now. In fact, let me go ahead and erase this fraction bar. It don't need to be that big. That'll be Z times sigma times the integral of, now what we have is r dr times pi times 2, all that over r squared plus z squared to the 3/2 power times k hat. Okay. What I'm going to do is do a technique of integration, a simple one though, because we have that 2r up there, we're in a good spot. So what we can do is we can say let u equal r squared plus z squared, then du will equal 2r dr. Now that I have that, I can use the 2r dr. I'm going to pull the pi way over to here. So I have pi z sigma over pi 4 pi epsilon naught times the integral of u to the negative 3/2 times du. That's going to give me z times sigma over 4 epsilon naught. Now, when I take the integral of u to the negative 3/2, that's going to be u to the negative 3/2 plus 2/2. So that'd be negative 1/2. So I'm going to get u to the negative 1/2 divided by negative 1/2, which is the same thing as multiplying by negative 2. And this is going to be evaluated from r equals 0 to big R. So I now get a negative 2, or well, the 2 is going to cancel out with the 4 downstairs. So I'm going to say negative z sigma over 2 epsilon naught. Y'all see that the 2 canceled out with the 4 in the bottom, leaving just a 2 there. The negative came from that integration thing too. And ultimately what I'm going to get is 1 over the square root of z squared plus r squared minus 1 over. Now, when you let r equal 0, the square root of z squared plus r squared just becomes the square root of z squared. And since it's a principal square root, a positive square root, that means it's going to be the absolute value of z. Now, you can probably figure out that the square root of z squared plus r squared is bigger than just plain z. Therefore, when I do the subtraction in those brackets, I'm going to get a negative number. So I don't generally want that. Also, I left off the K hat in both cases. I don't generally want a floating negative out front. So I'm going to eat the negative and flip the order of the subtraction. And I'm also going to distribute the Z through. So what I ultimately get is E is equal to, darn it, E is equal to sigma over 2 epsilon naught times, now in this case, we're going to get Z over the square root of Z squared plus R squared. Oops, I did it in wrong order. Hold on a second. I'm going to get 1 minus Z over the square root Z squared plus R squared, like that. All that in the K hat direction. And that is the actual electric field, a distance Z above the center of a disk, uniformly charged by a charge density sigma. Now, if you tried to say, hey, what would happen if Z was much bigger than R? Well, if that's the case, what you'd want to do is make the Z in the numerator right here, make that a Z in the denominator, a 1 over Z in the denominator, pull that 1 over Z into the square root, that'd become 1 over Z squared. Then you've got to distribute that over both terms under the square root, so that Z squared is going to become just 1 plus, now you're going to get parenthesis R over Z, close parenthesis, that squared. You can see that if Z is really greater than R by a lot, then R over Z is essentially 0. And you basically just get 1 minus 0. And that's going to give you times sigma over 2 epsilon naught. And lo and behold, you can see that sigma over 2 epsilon naught is exactly the electric field strength we got when the plane was infinitely large. Oh, I said that backwards. That's why I came up with a 0 when I wasn't supposed to. I meant if Z is really small compared to R. Sorry about that. So actually, to do it that way, it'd be smarter to leave the Z. Don't make the Z in the bottom. So yeah, if you let the Z get really small compared to R, then you're getting really close to it. As you get really close to it, the Z over the square root of Z squared plus R squared becomes essentially Z over Z. It's a little bit, of course, smaller than Z over Z because the R is not completely 0, but you can start to see where the sigma over 2 epsilon naught comes in. What you could do is you would use, in the back cover of your book, it's got a binomial expansion. It basically says that when you have 1 plus or minus X in parentheses raised to the n power, you can write that as a series of terms. Well, that's what you can do with that square root. And what you'd find out is you ultimately just get sigma over 2 epsilon naught times K hat. So, all right. So there's 2 uses. Well, one use of Coulomb's law in that integral form. And then I use the result from that to find the electric field at distance Z above a disk. So we've gotten that. Now the other thing is the law of Biot-Savart. You got to be able to do that as well. And what we found with Biot-Savart, remember, was we could do simple things. Like, remember, Biot-Savart says that B is equal to the integral of dB, which is mu 0 I over 4 pi times the integral of dl cross RP minus RDL over RP minus RDL magnitude cubed. So the reminder here is that we work this out pretty well, and we got a neat little coordinate system set up. And doing so, we were able to solve a class of problems that we might not otherwise been able to solve. So I can imagine, for instance, I'm going to make a slightly bigger line here. Maybe bigger than that. There you go. Okay, so let's imagine a current coming in this way. And then it arcs of some radius there. Then it goes out that way and arcs some other radius there. And then it goes out this way. Okay, now, if we wanted to, we could say, okay, the current's coming this way with this guy. Obviously, you'd go that way there. Oh, I didn't need that dark. Oh, I made it too small. Hold on a second. Okay, so we'll have the current going that way in that wire, 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 and then back out that way. So that's the way our current's going. And we could compute the magnetic field at this particular location. If I did that, what we would see is we'd realize for this straight part, notice DL vector would be basically negative dx I hat, assuming this is our x-axis and this is our y-axis, right? And RDL would be basically for that particular thing, it would be something times I hat. So when you, and RP, of course, for all of these is the zero vector. So you could automatically see from this that DL cross RP minus RDL is 0. The same thing with this one, because DL is going to be equal to dx I hat, or j hat, excuse me, and RDL is going to be something times j hat. So again, that gives you 0. Same thing for this one, and same thing for this one, and same thing for this one. Okay. Not only that, and I'm trusting my memory here, so you guys can look this up yourself. But if I remember correctly, we ended up getting B for a whole arc was mu 0 I over 2R for one complete circle. Okay. I'm going to put on here, check yourself. So when this first part, that first arc from say here to here, that's just a quarter of a circle. And as long as you know the current going through it and the radius, you can use that formula mu 0 I over 2R. And since it's a quarter of a circle, multiply it by 1/4. And if that's the R you're using, then that one's going to be R, and maybe the next one will be 2R, and maybe the next one will be 4R, and maybe the last one will be R over 2. But basically, that's how you're supposed to do the law of Biot-Savart for those simple problems. So those are fair game as well. So make sure you can do that. Anybody have any questions on that one? Let's try to I'm going to try to do a single loop of circle, okay, using the law of Biot-Savart, just to make sure y'all can verify or do this yourself. So let's draw my coordinate system again. There's my x-axis. There's my y-axis. What I'm going to imagine is that I have a circle. Whoa, that really went bad quickly. I think I'm going to use a cheat. Yep. See, I drew a perfect circle. So what I'm going to do is I'm going to say that's a perfect circle. I'm going to say it's carrying a current I in the counterclockwise direction. Okay. And what I would like to do is calculate the magnetic field right here at the origin. So B is equal to the integral of dB, which equals mu 0 I over 4 pi. And this, of course, is our solution. Mu 0 I over 4 pi times the integral of dl cross RP minus RDL over RP minus RDL magnitude cubed. RP is going to be the zero vector. I will draw right now that's RDL, and basically RDL changed it twice already. RDL is going to be equal to, if the radius of the circle is, let's say, big R, then this is going to be R cosine theta I hat plus R sine theta j hat. DL is going to be R d theta, and that's technically going to point in the theta hat direction, which I'll deal with in a little bit, but that's the direction that it points, which would be like that. Okay. It's perpendicular to the radial vector, and it's in fact 90 degrees ahead of it. So we've got that. We also know that RP minus RDL is going to be just negative R cosine theta I hat minus R sine theta j hat, because, you know, RP is just zero. That gives us, of course, that the magnitude of RP minus RDL is just going to be R. So that makes life a little easier. So now I can say B is equal to mu 0 I over 4 pi times the integral. Now DL we said was RD theta theta hat. I'm going to cross that with, basically that's just R hat times R. That's another way I can write that. And I'm going to do this just to see if it comes out to give me something kind of nice. And then all that will be divided by the magnitude cubed. So that would be R cubed. So right now we're getting mu 0 I over 4 pi. Notice the R and the R in top make R squared, and then the R cubed on the bottom makes it just R in the bottom. Now, if you take theta hat cross r hat, what you get is negative k hat direction. Ooh, theta hat cross r hat. So theta hat lays that way, r hat lays that way. Ooh, sorry about that, everybody. Notice I forgot the negative in here. That r hat was supposed to be negative r hat. I was getting the wrong direction. I knew something was up. So negative r hat is what that's supposed to be. So basically, if you take the theta hat, which I can draw, let's say over here. I'm going to change color pens real quick and try to draw this very quickly up here in the top right corner. My r vector, that would be r hat. Whoa. And then my theta hat would be right here. Okay. And you could write the r theta here, and this is 90-degree angle. From that, that's what I can see. If I cross theta with the r, then it points into the board, which into the board, if this is x and this is y, then k has to point out of the board or out of the paper. In this case, theta hat cross r hat points into the page. That'd be negative k hat. But we had a negative times the r hat. So that actually gives me a positive k hat. So I'm just going to put the k hat right here. Once I change it to red, I'm just going to put the k hat right here. And now all I've got is the integral. Whoa, there I go again. The integral from theta equals 0 to 2 pi of d theta. And of course, that's going to cancel out with the 4 pi in the bottom, because the integral of 2 pi of d theta from 0 to 2 pi is just 2 pi. So 2 pi divided by 4 pi just gives you 1/2. So in fact, I'm now going to get mu 0 I over 2 r k hat. So I was remembering correctly when I said, check this. But that's how that all panned out. Any questions on that? All right. Well, that's basically the things that I wanted to make sure I hit with you in response to preparing you for the midterm. So make sure you guys take your midterm on Thursday. As I told you, you can start up to 30 minutes early. You can finish up to 30 minutes late. The whole time you get for the test is only 1 hour and 50 minutes. What that means is if you actually started after 5:20, then you're actually not going to have enough time. You're not going to be given the full 1 hour and 50 minutes, but that's on you. So you got to make sure you, as a bare minimum, arrive on time. And then once you arrive on time, if you want the full 1 hour and 50 minutes, you are forced to stay an extra 30 minutes behind the normal class time just to get the time that you're allowed to take the midterm. So make sure you keep that in mind. Anybody have any questions about anything?
Yeah, I was wondering if, like last semester, there was a chance for a retake on the midterm. I don't plan to need it, but in the event that I did.
Yeah, there's I very rarely do that. So that's sort of a once in a lifetime thing. So I would hope that I never have to do that. If I screwed something up, I would definitely be forced to give you a second midterm or a second try. But I'm shooting for a clean one take, and no, we're not going to get a retest. So I definitely would not try to bank on that in any way.
Got it. Thank you.
No problem. Anybody else have any questions? Feel free to put down any constants you want. Constants like epsilon 0 or mu 0 or the K, if you like that version of Coulomb's law where it has the K in it, you can put that. The speed of light you might need. They normally, on the test, they normally give you like the mass of a proton or the charge of a proton, that kind of stuff, but it wouldn't hurt to have them on there if you did. But anyways, they normally give you that stuff on the test, so you shouldn't have to worry about that. But definitely you would need epsilon 0 and mu 0 and speed of light. All right, well, we're 4 minutes shy of the end of class, so if anybody has any questions that they haven't answered, now's the time. Of course, you're free to go to if you've gotten enough. Keep an eye out on your emails. I may send something to you at the last minute that maybe makes your exam a little easier or a little harder or whatever. The main thing is I want to make sure you guys, if I do send something like an email, I don't want someone to not get the advantage that the email gave them strictly because they didn't check their email. That's the main thing I'd hate to have happen. So always check your email at least first thing in the morning, and then a couple hours before class if you can on any given test day, just in case something comes up. All right, well, I'll wait here for the last person to leave, and other than that, you're free to go.
I have a question. I've been using Cholom's for all my equations and stuff like that. Do you think there'll be any issues, or should I actually look at the book and make sure they're all the same?
Yeah, I would definitely look at the book because Cholom's might actually give you some version of an equation that we don't allow on the equation sheet. That could bite you in the rear.
Okay, I'll
Okay.
take a look.
I'll look and see if I've got anything. I think I found the other day some equations. I'll look and see if I can find those now. If I can find them, I'll send them, and then that way you can have them typeset and just print them out if you want to or whatever.
I was going to write one up later this evening. If I write it up, I could shoot it to you in email, and you could check it for me.
Yeah, I can do that. Just make sure, like I said, only use the ones from the textbook that have the labels beside them. Plus, these two that I wrote in the red boxes, those are allowed as well. And who's this? Was that James I was talking to?
Hey, James. Yeah.
Yeah, no problem. Thanks, James.
I had another question as well. You said that don't want like full sentences and stuff. If we wrote like big R, little r and just radius on the side, so we have it, is that going to be an issue, or is that not allowed either?
That kind of stuff I don't mind too much. Just like I said, I wouldn't want any names that identify the law or the equation or the principle or something like that. But yeah, if you say I is current, that I'm not gonna put up a fight about that.
All right, that's everything I got. Thank you.
No problem. Good luck. I hope you all do really well. Everybody gets hundreds on the midterm. That would be awesome. I made me so happy. Anyone else? That's weird. I don't remember my alarm going off at 6:38, but clearly it's past 6:38 and I do have it set, so it should be. All right, well, I guess I'll go ahead and sign off then. Everybody have a good evening. Get prepared for your
Hang on.
test.
Can you check my chat message?
Yes, let me check that real quick. Oh, okay, I had it hidden. That's why I wasn't seeing any chats. Let's look over here. I wouldn't worry about any 241 ones at all. So yeah, that's fine. The 242 ones, I just try to make sure that you got all the ones that are from the from our 242 book. That's labeled anyways. But other than that, yeah, you're fine. Don't worry about it.
Okay, thank you.
No problem. I don't see any other, but anybody else put anything in there. So yes, diagrams on your equation sheet. You could certainly put a diagram for the version of Coulomb's law that I gave you, also for the version of Biot-Savart law that I gave you, also for A cross B, and also for A dot B. I wouldn't mind diagrams for those. Beyond that, I would not want any diagrams to be on your equation sheet.
Thank you.
The class starts, remember, at 5:20 on Thursday. But again, I've asked everyone to be willing to stay 30 minutes longer. That could mean you start 30 minutes early. It could mean you end 30 minutes late, but it could also mean you start 12 minutes early and finish 18 minutes late. All that's fair game. A couple of students have asked that they test at the testing center. Basically, that means you're supposed to take it on Thursday, but you're going to get a different version of the test. So make sure you make your appointment. According to one student tonight, they told us that they wanted you to make an appointment 48 hours in advance. So you need to try to make your appointment immediately for Thursday. So tonight, maybe first thing tomorrow morning, they might be able to accommodate you, but I would send out an email tonight and say, I would like to make an appointment for such and such a time on Thursday. Send them that email to whichever campus that you're wanting to do it, and maybe they can accommodate you, and then you can call back first thing in the morning and verify it or work out a different time that does work. It might be a matter of it works in one campus but not the other, so don't give up just because you can't get the time that you need, say from the Virginia Beach campus. Maybe the Chesapeake has that one open. All right, well, I'm going to go ahead and close up. It appears no one else has anything. So everybody, good luck. Please do well on your midterm. I hope you do awesomely, and I will see you next time. Actually, I will not see you until Tuesday of next week, unless you appear tomorrow at my office or at my Zoom meeting near the end. That's why I sent that Zoom meeting invitation out. Everybody can come in, like say 6:35 p.m. on Monday, Tuesday, Wednesday, or Thursday. And that'll be like an extra office hour in case anybody has any questions. All right, I'm stopping sharing and now I'm stopping recording. Bye, everybody.